Welcome to the video lecture on superelevation in railways. When a railway vehicle approaches a curved track, then it is subjected to centrifugal force. The centrifugal force tends to pushes the rail out of the circular track. In order to avoid this, or in order to compensate it, a superelevation is provided by raising the elevation of outer rail with respect to the inner rail, so that the resultant force is under equilibrium. Then this type of superelevation is called as positive superelevation. The reverse may also occur, that is, the inner rail will be raised with respect to the outer rail, then it is called as negative superelevation. This negative superelevation will be discussed later. This superelevation is also called as cant. Purpose of superelevation. Superelevation ensures better distribution of loads on both rails. It reduces wear and tear of rails. It provides comfort to the passengers and neutralizes the lateral forces. Equilibrium speed. The speed at which centrifugal force developed during the movement of vehicle on a curved track is exactly balanced by the superelevation provided. So in the picture below we can see F force. So this is the lateral force and this force is the centrifugal force. So whenever any object moves in a circular motion, the centrifugal force is developed. And we have a perpendicular force, downward force W, so which is the weight of the railway vehicle. And the dotted inclined line is the resultant force. So this resultant force will balance the adverse effect of the centrifugal force. So when it is balanced, then that speed is called as equilibrium speed. Cant deficiency. Cant deficiency occurs when a train travels around a curve at a speed higher than the equilibrium speed. It is the difference between theoretical cant required for such higher speed and actual cant provided. In such cases, we can see the centrifugal force as a horizontal red line and the weight of the railway vehicle as a downward red line, and green line is the resultant force. So green line is inclined and we can see it is more inclined to the outer rail. So when the resultant force is more inclined to the outer rail, then it means that superelevation is insufficient and it is called as cant deficiency. This can be avoided by moving vehicle at a design speed on a railway track. So the design speed is based on the superelevation that is provided on a railway track. Cant excess. So this is the just reverse of the cant deficiency. If the resultant force is much inclined to the inner rail than the outer rail, then it is called as cant excess. Cant excess occurs when a train travels around a curve at a speed lower than the equilibrium speed. It is the difference between the actual cant and the theoretical cant required for such a lower speed. Maximum permissible speed of the curve. It is the highest speed which may be permitted on a curve, taking into consideration the radius of the curvature, actual cant, cant deficiency, cant excess, and the length of transition curve. When the maximum permissible speed on a curve is less than the maximum sectional speed of a section of the line, permanent speed restriction becomes necessary. Cant gradient and cant deficiency gradient indicate the amount by which cant or deficiency of the cant is increased or reduced in a given length of transition. Example, 1 in 1000 meters that cant or deficiency of cant of 1 mm is gained or lost in every 1000 mm of transition length. Rate of change of cant or rate of change of cant deficiency is the rate at which cant or cant deficiency is increased or reduced per second. Transition curve. So transition curve is placed in all either railway or in a roadway before approaching a curved path. So this transition curve gives a gradual transition from a straight railway track into a curved portion. So the transition curve will be straight at the start of the straight railway track, and it radius gradually increases, or its curvature gradually increases and reaches the same curvature of the curved track when it approaches the curved path. What is the minimum super elevation that has to be provided? The super elevated surface should have a minimum cross slope as recommended for campus for purpose of drainage. So minimum super elevation provided. So when the super elevation is provided as equal to the camber. Maximum super elevation. Super elevation varies as the square of speed of the vehicle and the radius of curvature of the curve. So the trouble arises for a slow moving vehicle whose resultant force comes nearer to the inside wheel. The super elevation therefore should not be too heavy to make the railway vehicle overturn in such cases. Factors affecting the design of super elevations are the design speed of the vehicle, friction, maximum allowable super elevation, permissible centrifugal ratio. As already discussed, F is the centrifugal force and W is the weight of the vehicle and V is the speed in which the railway vehicle is moving, and G is the acceleration due to gravity and R is the radius of the curve. So the acceleration force is given as F is equal to WV square by 2G. So tan theta. So if we have theta, so theta is the angle between the resultant force and the centrifugal force W. Tan theta is equal to, or so which is same as, so you can see here below, so this horizontal line and this inclined line. So this inclined line is the super elevation that has been provided. So the horizontal line is the level of the inner rail and the inclined portion. So that gives you the centimeter or millimeter in which the outer rail is raised with respect to the inner rail. So that is equal to theta. So tan theta is equal to super elevation divided by distance between two rail is nothing but the gauge of the railway track. So super elevation by gauge. Super elevation is indicated as small e and gauge is indicated as capital G. So tan theta is equal to E by G. Also, we have seen theta is equal to the inclination between the centrifugal, the weight of the railway vehicle W and the resultant force. So tan theta is equal to centrifugal force divided by weight, which is equal to F divided by W. From this equation, so both are tan theta, so E by G is equal to F by W. So if we simplify this, we get E is equal to small e, super elevation is equal to GV square by GR. So for gauge, if we take 127, then E is equal to GV square by 127R. So 127 G is the dynamic gauge in millimeters. So R is the radius in meters and V is speed in kilometers per hour. Super elevation is in millimeters. So with all these unit conversions, we get the final equation as E is equal to GV square by 127 R, and substituting 9.81 for acceleration due to gravity. So after substituting all this, we have the final formula as E is equal to, that is super elevation is equal to GV square by 127 R. The maximum value of super elevation has been laid down based on the experiment carried out in Europe on a standard gauge for overturning velocity, taking into consideration the track maintenance standards. Maximum value of super elevation adopted around the world is 1/10 to 1/12 of the gauge. For broad gauge for A class, the limiting value of super elevation is 165, and for B and C class it is 165, D and E class 140, and in the meter gauges it is 90 and narrow gauge 65. All are in millimeters. So coming to negative super elevation. When the main line on a curve has a turnout of contrary flexure leading to the branch line, the super elevation necessary for the average speed of the trains running over the main line cannot be provided. In the figure AB is the outer rail of the main curve, and this should be raised in an higher elevation compared to the inner rail CD. For the branch line, however, CF should be higher than AE, or the point C should be at higher than point A. These two contradictory conditions cannot be met within one layout. In such cases, branch line curve has a negative super elevation, and therefore speeds on both tracks must be restricted, particularly on the branch line. The provision of negative super elevation for the branch line and the reduction in speed over the main line can be calculated as, so we know this formula, super elevation is equal to GV square by 127 R. So the super elevation required for the branch line is calculated by this formula. Then the super elevation E is reduced by permissible cant deficiency CD, and the resultant super elevation to be provided is X is the resultant super elevation that has to be provided in the branch line, which is equal to actual equilibrium super elevation E minus cant deficiency CD. The value of CD is generally higher than that of E, and therefore X is normally negative. The branch line thus has a negative super elevation of X. The maximum permissible speed of the main line, which has super elevation of X, is then calculated by adding allowable cant deficiency X plus CD. The safe speed is also calculated, and smaller of these two is taken as maximum permissible speed on the main line curve. What are the advantages of providing this super elevation? This super elevation permits high speed to be maintained on a curve as on straight without any danger, and thus results in increased volume of traffic. The vehicle keeps to the correct side. Super elevation less the danger of skidding. Super elevation of the pressure on the wheels is equally distributed along the railway track. Methods of introducing super elevation.